You may have learned that Pascal's triangle magically shows you the coefficients in binomial expansions and the answer to combination questions. But why? Expanding a binomial raised to a power often involves tedious distribution, but this triangle gives you the expansion's coefficients, which we call binomial coefficients, instantly. I found this really exciting when I first learned it, like a secret math trick, and the reasoning behind it is just as satisfying. Pascal's triangle was discovered long ago, yet its numbers are extremely valuable for the field of combinatorics and, of course, helping us high schoolers with expansions. It's made by starting with a 1 and imaginary zeros that surround the whole triangle, then summing neighboring numbers to create the number below. The zeros are so that the numbers on the side always have something to sum with. For the next row, you get a 1, 2, 1, then a 1, 3, 3, 1, and you get the gist. You can go on infinitely. We'll think of this triangle as a map. Yes, a map of paths. Why? You'll see soon. A step on a path goes from one row to the next, and it can either go one spot left or right. So, for example, we can take 3 steps left and 2 steps right to arrive at this 10. Can you figure out how many paths there are to this 10? Knowing the answer to this problem will help us find our binomial coefficients. There are many ways you can go about this, but the interesting thing is, the answer is 10. Okay, before I explain, just to be clear, I'll be calling all the numbers on the triangle as, well, spots, because numbers get confusing. The solution using Pascal's triangle is to recognize that the only way to get to a spot from a path is from either of the 2 spots above. So the total number of paths to a spot is equal to the sum of the number of paths to the 2 spots above. I know I'm saying spot a lot. You might see where I'm going with this, but let's walk through it. There's only one way to get to the first spot, so there's one way to get to either of the spots on the second row. Now, there are 2 ways to get to this spot, because it's 1 plus 1. There's 1 way to get here, 3 ways to get here, from either of these 2 ways, or this 1 way. Seems interesting. We're just getting Pascal's triangle numbers. Well, for both Pascal's triangle and our number of path numbers, we start with 1, and the rest of the numbers are the sum of the 2 numbers above. So the numbers of Pascal's triangle are the number of paths. I love how this simple connection exists, just because of the way Pascal's triangle is made. But this doesn't just help with finding paths on Pascal's triangle. This might be counterintuitive at first, but all different arrangements of the same number of steps left and right will always end up at the same spot. Like how if you were to walk to school from this house, all different arrangements of going 2 blocks up and 2 blocks across would get you there. Also, only one number of lefts and rights will take you to a spot. So we could frame the number of paths question as, instead of how many paths go to a spot, we ask, how many different ways can you arrange x lefts and y rights, with x and y being the number of lefts and rights you need to get to a spot. Does it make sense that that's the same question as how many ways can you arrange x a's and y b's? Because you can abstract left and right to represent anything. If there are 10 ways to arrange 3 steps left and 2 steps right, there are 10 ways to arrange 3 a's and 2 b's. So how many ways could you layer 3 scoops of vanilla and 2 scoops of chocolate? It's 10. How many 5-day schedules can you make if you want 2 rest days and 3 work days? 10. How many teams of 2 can you make, which would imply not selecting 3 people out of 5 people? 10. These are called combinations, which I mentioned at the start of the video. Normally, a combination is phrased as the number of ways you can choose R things out of N things, where the order doesn't matter. I'm not sure why we use N and R. The notation is N choose R, but here we're phrasing it as the number of ways we can arrange R A's and N minus R B's, A and B representing anything. The second phrasing is equivalent to the first because when arranging A and B, we have N positions to put the variables in, and we're choosing R out of these N positions to put one variable, with the rest of the positions automatically becoming the other. The reason we have to clarify that the order doesn't matter in the official definition is for some problems, it does make a difference. Like if we were asked, how many 2-flavor cones can we make if we have 5 flavor options? Strawberry then mango would be different than mango then strawberry. When you use the second definition, where we're arranging r things with n minus r things, we know that the r things are going to be the same, so it doesn't matter which order we put them in. In contrast, in the ice cream flavor example, the r things are different. So since the numbers of Pascal's triangle show you the total number of paths to the spot, and those paths are all possible arrangements of RAs and n minus RBs, which is the same as the number of the ways to choose r things out of n things, the answer to combination questions can be found in the number in Pascal's triangle where paths containing r rights and n minus r lefts terminate. And what we'll find is that finding binomial coefficients is a combination question. Just to be clear, we name spots on the triangle by giving them a row number and a position number. The rows and positions start at 0, remember that. For our combination problems, n is the row number and r is the position number. Notice in an arrangement of two things question, it doesn't matter which thing you assign to r or n minus r, because n choose r is always equal to n choose n minus r. See the ways to arrange two a's and one b versus two b's and one a, for example. That's why the numbers on either side of the triangle are the same. Let's do some practice. How many ways could you arrange 4 scoops of vanilla and 2 scoops of chocolate? We have 6 total scoops, since the cat ate the rest of them. So the row number is 6, and the position number is 2 if we made chocolate right, and 4 if we made vanilla right. That gets us 15 possibilities. Now, we'll explain why finding binomial coefficients is a combination problem. Well, notice in a binomial, we have 2 variables, so that's on the right track. When we raise a binomial like a plus b to a power, we multiply it by itself the appropriate amount of times. To do so, we need to distribute all a's and b's. So we have to multiply a's and b's together to get all possible sequences, like AA or AB. Each sequence simplifies into a term, and the sequences with the same number of a's and b's end up being the same term. For example, AB is the same as BA. In our final expansion, we put a coefficient to show how many of these like terms there are. But for larger powers, it gets harder to find all the terms. For example, we can start to list out all the possible sequences for a plus b to the 5. But there are too many to go through them all in a reasonable time. 32 to be exact. But wait, do we need to go through them all? We know there are 6 terms we can make, ranging from all a's to all b's. Now, we just need to find out how many times each of these terms show up. Hold up, we know exactly how to find that. It's in Pascal's triangle. We have 5 slots, so n is 5, and we go to the 5th row. Let's assign b to r. First, we need 0 b's and 5 a's. So r is 0, and we can go to position number 0. Then we need 1 b, so we go to position number 1. Then we need 2 b's, so we go to the 2nd position, then 3 b's, then 4, and finally 5. And so we get our coefficients. Wow. So we've answered a question and also learned a lot about combinations. I love how Pascal's triangle is so simple, yet it contains tons of useful information. It looks like wizardry. A little closer of a look reveals why patterns and connections to other topics exist. It's also approachable from many levels of math, since combinations are almost like a side topic, and finding connections between topics allows you to understand more about each of them. I have a collection of additional interesting information related to Pascal's triangle, like its connection to multiplication trees and the deeper inferences it reveals about combinations. But I realized it was too much for one video, so I decided I will include it in another one. If you're interested, look out for that. And of course, I am a learning student, so if there's anything you think would be valuable to add, or if I got anything wrong, I would be grateful for you to share. Thank you for watching. I hope you gained at least a little bit more appreciation for Pascal's triangle, and see you in future videos.